So the next lecture is on discrete models. You could also call it integer programming. And by the name, you already guessed that one of the constraints will be that the solution, part of it at least, will have to be an integer number. So this is the outline of the course of the lecture. So you see, integer programming is part of the discrete optimization. So it is not all the discrete models are integers, but it is a big part of it. So some problems, the solution that you are looking for the solution has to be an integer, has to be a binary value, or they have to be elements from a finite set. So these problems cannot be treated as the continuous optimization in which the variables can take any value, as we saw yesterday with the linear programming. So there are specific tasks and specific algorithms for this kind of problems. And here you have some examples of where these kind of problems appear. So for instance, let's say that you assign tasks to workers, so you cannot assign half a task or a quarter of a task, or scheduling shifts, or routing vehicles through a network, or selecting a subset of items, or whatever. So all these problems, you cannot use the standard continuous optimization techniques for this problem. So let's see a few examples. So let's say that you have a company that has to operate 7 days a week and needs a given number of workers each day. Then each worker can work for 5 consecutive days. So if you decide to assign a worker to a particular day, then the next 5 days he has to be working, and he has or she has a fixed weekly wage. So there is a cost associated to each one of the weeks. So the objective is to determine how many workers to start on each day of the week to meet the daily staffing requirement at minimum cost. Okay, so the variables that we will make the optimization will be the number of workers whose 5-day shift starts on the day I. Okay, so we have the days of the week from Monday to Sunday. So let's say you are planning for a McDonald's. So the attendance to McDonald's, I don't know how it goes with the week, but you can imagine that weekends behave differently from the daily from the weekly days. Then how many will start on Monday, how many will start on Tuesday, and so on. And there is a cost associated per worker per week. And DJ is the number of workers you require every day. So this is the demand, and this is what we are trying to optimize. So we will define a matrix that only takes values 0 or 1s, and this the ji element will be 1 if a worker started on day I is working on day j. And so you will have 5 ones in a row. So once a worker starts working on a particular day, the next 5 or the next 4 days will also be 1. Okay, so that is what is explained there. Okay, so you see that the number of workers that they start on every day has to be an integer. So either 1 or 2 or 3 or whatever, but it cannot be 2.5. So this setup of this problem is, okay, so you want to minimize the total cost. So the total cost per week is the number of workers that start every day of the week times the cost of each one of the workers. And then you have to fulfill the needs of the store or whatever. So for every day, so these are days, the number of workers is working for that day has to be larger than dj, and the number of workers working this day is distinct. So it is the matrix times the number of workers starting on each one of the days. And then we have this constraint that it has to be the number of workers starting every day has to be an integer larger or equal to 0. Okay, so we will not solve this problem for the moment. Some other example is this one, in which you have a depot. So you are a delivery company that has a depot, and you have several customers. And you need to deliver your goods from to each one of the customers using a single vehicle or multiple vehicles. So depending on what is the version of the problem, you may have one or multiple vehicles. And the goal is to find the shortest possible route that starts and ends in the depot, visits each customer exactly once, and minimizes the total travel distance or cost. So this is a generalization of the traveling salesman problem. So here you have multiple solutions, for instance, here. So you may have one vehicle making this route, some other vehicle doing this route, and so on. So how to formulate this? Okay, so let's say that we have a number of nodes, and node 0 will be the depot, and all the others will be the customers. And then you have a distance matrix that tells you what is the cost of traveling from node I to node j. And then the variables that we will act upon will be this xij, that is 0, 1 if the route goes directly from node I to j. So here in this example, this edge would be 1, but this one would be 0 because we are not traveling from here to there. Okay, so this is 0, this is 1. And then the objective function is the distance matrix times your vector of traveling. So whether you are going from I to j. So this is what you want to minimize. And each customer is visited exactly once. So that is the sum, customers are I. So the sum for all xij's, sum over j, has to be 1. And enter each node only once. So it is the sum of xij, but now over I, not over j, has also to be 1. So we have equality constraints. We have the depot constraint. The depot constraint is that you depart from the depot and you return to the depot. And then there is this subtool elimination that we already presented with the traveling salesman problem. That is, you don't want to create cycles here so that you don't go to the depot. So you don't want the cycles to be disconnected, the routes to be disconnected. They have to be a continuous route, and that can be done with these extra auxiliary variables UI, and UI will be the position of node I in the route, and it has to fulfill this constraint. And the constraint is not obvious, it is not big, but it prevents the creation of these cycles. And here again, the variable that we are optimizing, so the variable can only take values 0 or 1. So either you go from I to j or you don't, but you cannot do it 0.1. Okay, more examples. So this is a version of something that is k-means. Have you seen k-means? Yeah, you saw it yesterday with me too. And k-medoids. So the difference between k-medoids and k-means is that in k-means, the centroid does not need to be one of the points of the set, but in k-medoids it has to be one. Okay, so let's say that you have 10 neighborhoods. So you're in a city, you have 10 neighborhoods, and you want to place 3 ambulance stations. So not all the neighborhoods will have an ambulance station, and each neighborhood has to be assigned to one and only one of the stations. And the goal is to minimize the total response distance between the neighborhoods and the assigned stations. So the constraints is that the stations can only be located in existing neighborhoods. So you cannot take this kind of Chinese approach where the station could be in the middle of nowhere. And every neighborhood has to be served by one selected station. So the thing is, which of the points, so I am given 10 points, which of these 10 points I assign to be a station or not. So this is a more formal formulation of that. So we have 10 neighborhoods, we have all the distances from neighborhood I to neighborhood J, and we have these decision variables that are take value 1 if an ambulance station is placed at that neighborhood, and otherwise it is 0. An Xij is 1 if neighborhood I is assigned to the station at J, or 0 otherwise. So again, the two decision variables, Yj and Xij, will be 0 or 1. So what we want to minimize is the total response time. So it is again the distance matrix times your assignment. So it is the same as in the traveling salesman. And each neighborhood must be served by one station. So the sum of Xij has to be 1 if you sum over J, and this has to be true for all neighborhoods. And the assignments are only allowed to select the station location. So Xij has to be smaller than Ij. There are exactly 3 stations, so the sum of the Ij's has to be 3, and the variables are binary. And again, we will not solve it, but you see that there are problems that are discrete by nature. This is another example. So you're given a knapsack, and you're given a set of items. Each one of these items have some weight and some value. So for instance, the weight of this one is 9 kilograms, and the value is $1.11 per kilogram. This is 12 kilograms, and the value is $0.58 per kilogram, and so on. So the goal is to have a limited capacity of 15 kilograms, which are the items that I should take to maximize the value of my capacity. And then probably the solution is this tool that we are showing, on how to formulate that. So you have, for each one of the items, you have a value, and this xi takes value 0 or 1, depending on whether you take it or not. So what you want to maximize is this sum. So it is the total value of your choice, and it is subject to the capacity constraint. So the weight times whether you take it or not has to be smaller than something. Good. And again, it's a discrete problem. And I think this is the last one that we will see. So let's say that you have a universe of elements that you want to cover. So you have a set of elements, and you have some subsets, not all of them, but these are some subsets. So let's say that S1 is these 4 elements, S2 is these 6 elements. They don't need to have even the same amount of elements in each one of the subsets. And each one of the sets, of the subsets, they have an associated cost. And then what we want is to find a sub-collection of subsets. So which are the subsets that we choose, such that we cover the whole set. So this is the first condition. So the union of all the sets that we choose is the whole set. And the total cost is minimized, because taking each one of these subsets, they have a cost. So we try to minimize that cost. So again, we try to minimize the cost of our choices. The choices will take again value 0, 1, depending on whether we take that set or not, subset or not. And this constraint means all the elements are taken. So this Aij is 1 if the element Ei is in that subset. So in subset J. So this condition means you have to cover the whole set. Very good. So this is a combinatorial problem. So you have to try all possible combinations and see which one has minimal cost. Okay, so when you solve this kind of problems, there are some two families of algorithms. So for integer and binary programming, that are the ones we have presented so far, you have what are called exact algorithms. So the exact algorithms, they come in a number of flavors, but they guarantee finding the global optimum. Okay, maybe if the problem is too large, because you have to try many possible combinations, it may take a lot of time to find the optimal solution, but you can find the global optimum. And these are the different algorithms. We will see them. So branch and bound, branch and cut, dynamic programming, integer linear programming, and so on. The other set of the other family of algorithms are these greedy or heuristic algorithms. So they are faster than the global ones, the exact ones, but there is no guarantee of optimality. So they will find a good enough solution. Especially this is good for very large problems, but they are not guaranteed to converge to the global optimum, but sufficiently useful optimum. We will see again each one of these algorithms in more detail, so I will not comment on them now. Okay, any question here? No? Very good. Then let's say that we have this problem, so that we many of the problems we had before, they could be formulated in this way. So it is we want to minimize a linear function, so we can look at the other ones. So this is exactly that. This is exactly that. And again, this is it is a matrix times a vector, but a matrix times a vector, if you put the matrix in a long form, it is again a vector times a vector. And so all of them, they are formulated as the sum of the elements of your solution of this thing. So the sum of the elements of your solution, subject to some inequality constraints, and that the variables that you are optimizing there have to be integers. And then we will relax the problem. So the relaxed problem will be exactly the same, but now the solution does not need to be an integer, but it can be a real value. So we can take any continuous value. So this is called, so this is a linear problem. So now this one is a linear problem. So it is called the linear programming relaxation of the integer linear programming. So this is integer linear programming, and this is the linear programming relaxation. So it is the relaxation of the previous one. One of the first algorithms that we will see is this one, branch and bound. But there's a mistake here, it should be branch. So branch and bound is a general algorithm for finding these optimal solutions. And what we will do is to explore the state space, so the feasible region, in following a tree. And each one of the trees of the branches of the tree will give us some bounds on what the solution is. So I think it will be more clear with an example, and we will give it later. So let's say that you have some function to minimize or maximize. You have a feasible set that is included in set n. So this is a set of integer numbers, and the solution space 3. Each one of the nodes will present a sub-problem with some more constraints than the original, and the root node corresponds to the original. So you start with the original problem, and then you start subdividing more specific sub-problems. Okay, so let's see an example. So this is the general procedure. So you start with the general problem, and in this general problem, you discover that x1 for the relaxed general problem, you discover that x1 is 0.3. So 0.3, because 0.3 is not an integer. So either it is smaller or equal 0, it is larger or equal 1. So that will give you another problem with an extra constraint, and another problem with an extra constraint. And then this applies, this continues. So now you discover that P2, in this P2, you discover that x2 is 0.2, and then again, either it is smaller or equal 0 or larger or equal 1, and so on. And in each one of these problems, you will have bounds. Okay, so let's follow this thing. So you start with the root problem, and you place it in a list of live nodes, so problems to solve. And while that list is not empty, you choose one problem from the list, and here there are multiple choices. So when you take the one with the best bound, or you try to explore this tree first in depth and then in breadth, or you choose your strategy to choose which problem to solve at that moment. You solve a relaxed sub-problem of that node, and then you solve for each one of the problems, you solve the relaxed one, and you get the non-integer solution, and you get the bound. And then there are multiple things here. So you stop that branch, so this branch was not continued, if the problem is infeasible. So there is no solution to this problem, or the bound is larger than the upper bound. The upper bound, I forgot to say here, it is the best objective value found so far. So let's say that you are minimizing, so the best value that we have seen so far. And the first time you set it to plus infinity. So if the bound that you have found for this problem is larger than the best you have seen, then there is no point in trying to continue, because anyway you will not find anything better. And the solution is, let's say that the solution is feasible. So you have found this solution. The solution is feasible, but the function evaluated there is smaller than the upper bound, so you update your bound. And otherwise, you create two childs, like we did here, in which you put, so we said here, x1 is 0.3, so, but 0.3 is not an integer, so you create two extra bounds. One in which you bound, so you put two constraints, one in which one is smaller than rounding down, and the other one in which it is larger than rounding up. And then you have two new problems in your list to solve. Okay, so let's see an example. So let's say that you are the owner of a machine shop, And this machine shop, you want to purchase two kind of machines, these presses and lathes. Lathes son tornos, presas y tornos. So each press contributes to the daily profit with $100, and each lathe contributes with 150. But then there are some constraints. So the total budget that you have, the floor space that you have, and then the prices of each one of the kind of machines and the surface that they occupy. So your goal is to find the optimal number of presses and lathes, and both have to be integer to maximize the profit. So we want to maximize this, subject to the constraints of budget, the constraint of space, and the constraint that they have to be integers. So without this integer constraint, it would be a normal linear programming problem that we learned yesterday how to solve. Okay, so the first thing is, because we have only two variables, I have drawn the feasible region. So we have two constraints. One is on budget, that is the blue one. The other one is on space. So for this region, you are limited by budget. For this region, you are limited by space. And then we solve the sub problem without any constraint. Okay, so without any constraint. So we want to maximize this thing, subject to this constraint, but I mean no integer constraint. So with no integer constraint, this is the solution. 2.22, 5.56, that we know it is this one. So it is this corner. But again, we learned that yesterday. So if you evaluate that function in this corner, the value you get is 1055. Okay, but this is not integer, so this is not feasible. Or this solution is not feasible in the original problem. Then you can, for instance, round down both solutions. And actually, why round down? Because if I round that, or I round to the nearest integer, so let's say the nearest integer is 2 and 6, but 2 and 6 is here, it is not visible. So the nearest integer solution that is visible is this one. It's 2 and 5. So now, and I evaluate the function again. So I don't know where the optimum will be, but I know that the upper bound is 1055. So the solution I will find for sure cannot be better than that, because that was the optimal solution with non-integers, but you are not allowed to make integers. So it cannot be larger than that. So that gives you an upper bound. And you also have a lower bound, because I know, okay, at worst, whatever I explore anywhere else, at worst, I have a solution that is 950. So if you find anything that is below 950, disregard that solution. Okay, so the first problem here, we have solved it without the linear, the integer constraint. Okay, good. But now we said, okay, this is not feasible. So I will focus in one of the solutions, one of the variables. So let's say x2. And for this x2, I create two subproblems. One in which, okay, the solution is 5.5. So either it is smaller or equal 5, or it is larger or equal 6. Those are the good possibilities. So now you draw the feasible region for this one. So for this one is this two regions. So we have now constrain x2 to be either below 5 or above 6. So the first subproblem, this is the feasible region. And for the second subproblem, it's only this one. Okay, then let's solve this one. So let's solve this one without constraints, and then we have 2.55 and 1,000. But this 1,000 is okay. So let's leave that solution, and then again round down so that we have this solution, and then you have 50. But let's explore this one. Let's explore this one. The solution is this one, 1,033, and the lower bound. When you round, the lower bound is 1,000. And now we compare these two problems. So this problem, the upper bound of this one is smaller than the lower bound of this. So I don't need to continue exploring this terms, because in the best case, whatever I find here will be worse than this. See? So I don't need to continue exploring that. Okay, so we continue exploring this one, and now we update the upper bound. So the upper bound here is 1,033. That is smaller than this one, so we lower the upper bound. Okay, now again for this one, the solution was x2 equals 6. So now see, x2 is an integer, and the one that is not an integer is x1. x1, the best solution was 1.3. So again, we have two subproblems. One in which x1 is smaller than 1, or x1 is larger than 2. Larger rate. So same here, smaller than 1. And then we have the original constraints, x2 larger c, and the new one, x1 smaller or equal 1. The solution is this one. And this is the rounding. And for this one, x1 larger than 2, x2 larger than 6. So let's look at we're in this branch. We're in this branch coming from here. So x2, x1 larger than 2, and x1 larger than 2, then it's not feasible. So this even we don't have to solve. We see here that it is not feasible. So the only one that we have to solve is this one, and we already have the upper bound and the lower bound. So we update the upper bound, and now it becomes 10,025. And here, x2 was not integer again. So now we have again two subproblems. One in which x2 is larger than 7 or smaller than 6. Again, this is not feasible because we were here. So x2 larger than 7, there is no solution there. And this one that we have to solve, the solution is this one, 1, 6, and now everything is an integer, and so we have to install. We have found an integer solution of it. And the value here is 1,000, and then we update our upper bound and lower bounds both to be 1,000, and that is the final solution. Okay, any question?